All right. Thank you for coming back after lunch. And thank you to everyone who voted for the posters as well. 2 sessions down, 2 to go, and we'll be diving into a little bit more technical content. And the first speaker we have is Dr. Vladimir Lisitsyn from the survey. Vlad will be presenting critical minerals in Queensland deposits and exploration in mineral systems footprints. Welcome, Vlad.
Okay, good afternoon. In this presentation, I will briefly introduce a pretty major work program of GSQ, the program aiming to characterize signatures and footprints of Queensland mineral deposits with a particular focus on the critical mineral endowment. So this is a pretty sizable body of work we've been doing for more than 5 years. And in fact, this entire session until the afternoon tea is going to focus on certain aspects of this program in some detail. So I will give you just a brief introduction. But first of all, before we go into details, I just want to set the scene and explore the question why we bother to undertake this work, because it's a massive effort involving multiple people. After all, why characterize signatures of known deposits after all they're known? Basically, we are trying to address 2 major challenges of exploration and mining. Challenge number 1 is understanding what's inside the ore. And surprisingly, there is little information on many aspects of ore geochemistry and mineralogy, and in particular in terms of their critical mineral content. So whatever is now critical minerals quite regularly were niche commodities, and even for some major deposits, there is little information in the public domain to characterize which critical minerals are there and which of them could be economic to mine. And also, multi-element geochemical and mineralogical signatures of deposits can be very useful for early identification of the types of mineralization, and that has very significant exploration implications. And there is a significant exploration challenge about how to be more effective in mineral exploration in greenfields. And the industry is not particularly great in effective navigation through distal footprints of deposits. So once you found the deposit, that's easy, but when you intersect some distal parts of obscure alteration, make an early correct decision what it is representing and which way to go is far from easy. So first I'll stop on critical minerals and the ones which are particularly poorly understood. So half a dozen of critical minerals are mostly present in potential core or byproducts. And well, in particular in Queensland, it's germanium, indium, gallium, cobalt. So there is some information in the public domain about the general content, but not enough to make sensible decisions. And so when we started this program, it was quite surprising to see that we couldn't even properly, confidently talk about, say, germanium and indium content in Mount Isa lead zinc deposits. And these are some of the largest deposits on the planet. And that underpins our comprehensive geochemical characterization approach. If there is an element of potential interest to somebody, we analyze it. And it's not the lack of key information on ore geochemistry, in particular for critical minerals. It's not just Queensland-specific problem. It's not Australia-specific problem. There is a global challenge. And in fact, for the past 4 years, there is a global critical minerals mapping initiative between Geological Survey of Australia, United States, and Canada, and a major effort of that 3-country alliance is to actually go out and characterize critical minerals in ores. And GSQ was a major contributor of that program. So in fact, most of the data on Queensland ore deposits came from this program of ours on characterization of ore geochemistry. So this is a general overview of what we have done so far. So overall, we have characterized to some extent more than 100 deposits, primary and secondary mine waste. mostly focusing on North Queensland, Northwest, Northeast, because they are the premier mineral provinces. So we are doing a consistent characterization workflow for most of them. On primary deposits, it includes continuous core scanning, whole rock geochemistry, and getting more and more increasingly in microanalytical techniques. A separate body of work which we trialed back in 2019 on mine waste characterization now is a major national program. So courtesy the group of Anita Pabaka folks and Benjamin Hines is going to summarize results of that work. And I'm going to focus in a little bit more detail on Northwest Queensland, and other members of my team are going to cover other areas and other aspects. So one of the key, well, certainly the key and first step in this program of ore and alteration characterization is actually acquisition of the right samples. When we started the program, the original idea was very simple. We're going to go to our core store, we're going to select samples, analyze them, and that's pretty much easy. And as it turned out, we didn't have sufficient collection in our core store, and the large part of the past 5 years was spent actually going out to mining exploration companies and acquiring well-characterized, representative drill cores from multiple deposits and doing our work on that. And right now, it is a major resource, not only for ourselves, but our numerous collaborators in research and in the industry. We're doing whole rock continuous characterization of drill cores from as far away from mineralization as possible and into the ore. So the cornerstone, in addition to our workhorse HiLogger, which has been with us for 15 years, we're using campaigns of continuous XRF scanning. So we just finished a program with Mineralizer instrument scanning 10 kilometers of drill core this year. And we're analyzing thousands, multiple thousands of ore and whole rock and alteration and host rock samples for multi-element geochemistry. And we're increasingly going into microanalytical techniques. It's something which is typically the realm of university research students. But as we go to try and characterize critical mineral endowment, critical mineral opportunities, and the problems of distal mineral system footprints, it becomes quite clear that at some distance from mineralization, we are losing the signal. And we do need to go to the level of microanalytics, mineral chemistry, isotope geochemistry, and we have a pretty substantial talk by my colleagues who are going to cover what we're doing in the microanalytical space. And one part where we're just getting started goes into isotope geochemistry, and there are good prospects in that area, including in the area of provenance characterization, provenance studies identifying the sources of metals. So that's something which we're going to trial in the near future, going into mineral chemistry of ore minerals and isotope chemistry. So I'll take you briefly through some major mineral systems and deposit types in Northwest Queensland. So there are 5 major mineral system types which underpin the minerals industry in the state. So starting first from iron oxide copper gold deposits, that's a particularly diverse family with a large number of individual deposit types and styles. And that's where we actually became aware of the importance of doing extensive sampling and extensive studying of individual deposits because different deposits of the same type are so different, to the extent that it's impossible to meaningfully talk about critical metal endowment of iron oxide copper gold deposits in Queensland because some of them are extremely important and productive and some are not. And before doing the studies, for most of these deposits, this information was simply not available. For many of them, it didn't exist. So this is an indication of just how variable iron oxide copper gold deposits in the region are. So quite often opinions of people are based on general overview papers, quite good papers, and so we were under the assumption that most of deposits are just like Ernest Henry, and when we finished, well, we haven't finished our work, but after studying 25, 30 deposits, we came to realize that there is just one deposit with exactly that geochemical mineralogical signature, and everything else is different. And that has serious implications both for exploration and for potential extraction of critical minerals from ores. So, for example, overall, we can say that iron oxide copper gold deposits are consistently enriched in cobalt and to some extent in light rare earth elements and rhenium, but this is far from consistent. So, for example, rhenium is, in general, on average, is significantly enriched. In Ernest Henry, it's enriched much more than in most others, and so there are unique outliers with concentrations of rhenium which could allow to classify them as primary rhenium deposits. Cobalt, that's a particularly consistent element, and that's significantly enriched in most deposits, but again, it's far from uniform. So in some deposits, the average grades are consistent with what could be considered potentially mineable economic byproducts. Some other deposits have much more modest enrichments. And we're also doing more work on microanalytical characterization of the distribution of cobalt, and that's a subject of research we're doing jointly with both University of Queensland and JOGMEC in terms of the metallurgical processes to unlock it. But at least now we have a good baseline to build our work on. Sediment-hosted copper in the Western Mount Isa, another major copper deposit type. It has quite significantly different mineralogical and geochemical characteristics. So in multi-element geochemical signatures, they're quite easily distinguishable by the degree of their enrichment. And in terms of similarities with ICG deposits, the most consistent element, critical element which could be of potential significance is cobalt. Same as for ICGs, the enrichment of cobalt is far from uniform. In many deposits, cobalt concentrations are getting to the grades which are potentially economically extractable. And it's also a matter of ongoing research to investigate the modes of occurrence of cobalt and how to actually unlock the potential of cobalt in these deposits. So in fact, it is quite likely that the largest cobalt deposits in Queensland have already been discovered. It's just we're not recovering cobalt from them just yet. Sediment-hosted zinc-lead deposits, typified by Mount Isa and George Fisher Hilton. So their multi-element geochemical signatures are somewhat similar to those of sediment-hosted copper deposits. And of particular significance for this conversation is critical mineral enrichment. So two elements particularly stand out. It's germanium and indium. So both of them are significantly enriched to the concentrations at which they are actually getting extracted elsewhere in the world. And in particular, we were pleased and excited to characterize germanium concentrations. And a word of caution, which we became aware in the process of work, traditional multi-element geochemistry grossly underreports germanium, so we had to go to a significant length to properly characterize germanium content of lead zinc ores. Phosphorites, when we started for the program of characterization of critical mineral content of Queensland deposits, there was general information that phosphorites are generally enriched in rare earths, and there were a few overview papers in the global literature suggesting that Cambrian phosphorites are not particularly enriched in rare earths. We needed to go and check it out, and in fact, most of our phosphorites in the Georgina Basin are significantly enriched in rare earths, in particular in yttrium and other heavy rare earths, and the enrichment is far from uniform. We have some deposits like Ardmore, which are enriched by an order of magnitude compared to others. and we're getting to concentrations of rare earths sometimes exceeding 1 weight%, and there are metallurgical processes which can be used to extract rare earths from phosphorites. Mineral systems in northeast Queensland. This is our relatively recent addition to the geographic extent of our studies. I'm not going to go into any great extent because Courtney Dinaram is going to cover this region in some more detail. It's sufficient to say that it's a very diverse combination of mineral systems and deposit types, and some of them have very, very significant enrichment in some critical elements, in particular indium. Now, a very brief introduction to the concepts of distal mineral system footprints. That's our relatively our recent addition. So we have done a few studies with external collaborators like University of Tasmania Coates, and we're doing more and more of this work ourselves. We're trying to characterize on the basis of well-characterized drill cores and samples around known deposits what a near-miss scenario looks like. So what does it look like to be 1 kilometer away from Ernest Henry? What does it look like to be about 100 meters away from Ernest Henry? And as it turns out, so this is a far from a trivial problem. And sometimes you can see signals you can trace to the major deposit hundreds to thousands of meters away. Sometimes we're still struggling to see that we are within 20 meters. And that's the realm where it becomes increasingly commonly understood that we are doing lots of bulk geochemical mineralogical characterization, but there are logical limits of how much you can take that. At some point, we're simply going to lose the bulk signal. At some point, the signal of mineralization is going to be as strong or as weak as natural variability in normal rocks, and that's why we need to use much smarter techniques. That's why we're going much further into microanalytics, mineral chemistry, and isotope geochemistry. So I'm sincerely hoping, reasonably sure, that we're going to have something to discuss in this realm in Digging Deeper 2024. So our aim in this program is to do massive amount of new data acquisition and to release it as soon as we possibly can. So as soon as a data package is ready, the quality and completeness is such that it allows external use. We're trying to package it up and release to the outside world with minimum interpretation. So there is a substantial number of data packages and some earlier reports which have already seen the light of day. More are certainly along the way, and we're going to have a large data release session in the middle of 2024. Just watch the space. And even before we're ready to release data packages, we're trying to engage more and more into face-to-face discussions, engagement with the industry, including quite often when this is still work in progress. So we are running quite regular industry workshops. Two most recent ones. One was done in Cloncurry and Mount Isa as part of the SGA conference with Geoscience Australia in August, with great feedback from international audience. And the most recent one was yesterday at Exploration Data Center. We had 40 participants and 30 external people, mostly from industry. So we shared with them what we're doing right now, showed the drill corp, which we just recently acquired. So that's something which we are finding enjoyable to share with the outside world, and people who attend these events find it useful. So I'm using this chance to thank the Mineral Systems staff who made that event and similar events a great success. Thank you all. You know who you are, and thank you to the participants who came and participated in that. Your feedback actually keeps us going and helps us moving on with further work. And this work could only be possible in collaboration with multiple external research organizations and industry partners. There are precious few major universities with whom we're not working right now, and quite often it's still work in progress. We are getting increasingly into the meaningful collaboration and away from pay and forget model. and I can assure you that it works much better this way. And our interactions with industry are increasingly productive and helpful, and the word is getting out, and companies, exploration mining companies, are more and more happy to donate their drill core, to share their knowledge, and that's what makes it possible for us to build that pretty unique collection of reference drill cores, reference data sets. It's something which is for common use. We have a queue of companies who are queuing up for our drill cores, and this is a major research resource for research organizations. So thank you all for helping us building up this resource. And I shall leave it at that. So for the rest of the day, for the rest of this session, I will leave it to other members of my team. And thank you.
Thanks very much, Vlad. The next presentation will be delivered by Courtney Denarum, one of the senior geoscientists from GSQ, and the title of Courtney's talk is Characterising Deposit Signatures on Footprints in North East Queensland. Welcome, Courtney.
Oh, I can't see that at all. Oh well, saying I'm winging it. It's lovely to be here this afternoon to talk to everybody. I think this is the first time in a number of years I've been able to present at such a big audience on the work that I've been doing in North East Queensland. For those who were up in Mackay this year and Charters Towers last year, you might have heard of what we've been trying to do in North East Queensland, but it's very much along the lines of what Vlad was talking about and all the work we've done previously in North West Queensland. So to start, I would like to acknowledge all the logos here, even if companies currently don't exist, all the people who I've talked to and worked with, anybody who's ever packaged up core and tried to get on a truck, anybody who's read 100 emails from me politely nagging, please, 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 can I get core? It is so important. And as I go through this talk, you realise why in North East Queensland it's actually a bit more complicated than it was in North West Queensland to try and get the right sort of samples to do this research on. Shout out to the people who know someone who knew someone who worked there back in the 70s, and there might be some drill core under a tree, has been really helpful in some old tin and gold fields. And shout out also to the mineral systems team here at GSQ, especially Frederick, who has done a lot of the heavy lifting in the last 2 years for the sampling on this drill core. So I just wanted to give a bit of an outline to the project rationale and aim and what I'm trying to do as part of this 4-year project in North East Queensland, the workflow that's involved, and then the work currently that I'm doing in intrusion-related gold deposits. So my talk is a bit of high level compared to the talk this afternoon. We're about 4 years behind where we are in North West Queensland currently, so we'll get there. There's a bunch of words on the screen. Really the main aim of how we got the funding for this project was under the New Economy Minerals Initiative, so really looking for critical minerals in North East Queensland. And we knew that we had some deposits that were delightful, so tin tungsten, tungsten moly bismuth, and then we also had anecdotal sort of information that some of the base metal deposits might have indium, or there's potential for, germanium in these sorts of deposits. So it was really important for us to sort of sit down and start the project, essentially how we did in North West Queensland, to look at this. So we decided to start with an inside-out approach. It was really important to characterise the main deposits in the region. It would be great to step out into proximal and distal, but to be honest, a lot of the information just doesn't exist on the deposits before you try and figure out what it looks like 500 metres away. And cool. So this is the area that we've covered. North East Queensland's really big, if you didn't know. So there's a lot of big deposits. There's a lot of spatial extent of these mineral systems. So we had to sort of pick and choose where we were going to focus our work. And that was really dependent on which companies we were able to get drill core from. So what was the existing state of play in North East Queensland? Well, there's numerous historical gold fields and tin fields with minimal exploration, modern exploration. So what does this look like? Well, it looks like lots of handwritten notes with 7% indium and a bunch of comments about tin grade, and lots of comments about, well, we threw out the wolframite in the waste pile, but not an actual, a lot of modern data. So that was really hard, and also there wasn't a lot of recent drilling on these. So to do any sort of analytical work on these deposits, you actually had to go out and either get samples, from the mullock dumps and from in situ in the pits to do this work. Anybody who's looked for gold in Northeast Queensland would know that there's limited historical assay data, and honestly, if you're looking for gold back then, you just assayed for gold. If you're lucky, you might have assayed for like arsenic, maybe silver, maybe copper, but 5 elements and you were well and done and dusted. So in between having a limited public assay database available, also because the goldfields have been under tenure for over 100 years, a lot of this information has never been made public. So we're really not starting from the same playing field as we will be for Northwest Queensland, where some of the information has been made public before we started doing this research. And honestly, we didn't really have a lot of drill cores from Northeast Queensland. As per usual, I was shocked that we didn't have drill cores from some of the major deposits and places that I just assumed we would have had at least one drill core. So really, the main side of this project was just trying to get the right rocks to do the right sort of work. So what were the project aims? Like I said, it's getting well-located drill cores and samples with all the metadata that you would need to know where it sits in space. So there's been a lot of really, really fantastic research work done by numerous universities under big and Mora projects on these deposits in Northeast Queensland. But a lot of the time, the sample would be like, so it's from Mount Lation, which is well and good, but how far, in what drill hole, and where does it sit into the context of the deposit? So we really made a focus on trying to go through old drill core and get all the metadata, everything we could, to be really confident about where it sits before we started doing any sort of work on it. And then we focused on 2 types of data collection. One was doing multi-element geochemistry, and the other was doing hyperspectral drill core scanning. So it was really important for us to get new modern techniques on these drill core, expanding the existing geochem, and also doing lots of non-destructive work. So for a lot of the drill core I got from the Herberton region, which is a tin province, it was AQ and BQ for those who know how small that is, but it's about this big and you can't do much with it, you can't cut it up, and if you want to do any geochemistry, you're destroying all of your sample material. So we had to be a bit innovative of how we tried to collect the data that we needed to interpret these systems without destroying the only material that's existed. And one of the part of the work was identifying samples for further characterisation work. So there's a few posters that you would have seen in the lunchtime session from 2 students. One is Avish and one was Shin from UQ, and they've been working on samples that were acquired as part of this reference collection work and has gone on to do more detailed work. So that's one of the big benefits of having these samples is we can have the questions and then we're able to pass these on to students and our other collaborators to try and answer them. But that was only a side part of this project because really we're trying to get the spatial coverage across Northeast Queensland. So what did the project workflow look like? Well, as Vlad alluded to in his talk, looks like this. Looks like me sending a lot of emails to a bunch of people in this room over and over asking really nicely, hey, I'm working on a project in Northeast Queensland and it would be great to talk. Got some ideas about the area you're working in. Do you guys have any rocks? And then time goes by because life happens, we're very busy, and I email people again, say, hey, it'd be really great. So this goes on for a while. So I had an interesting comment at the workshop yesterday about, it'd be really great and good to start core acquisition earlier in the project. I'll be honest, I started it like day 1 of the project, and just things take time. So, and that really reflects on the places that we study during our project. So it's just part and parcel, it's life. But when it goes well, I get a response and I'm like, sure, what would you like? So we work really closely with the geologists on the ground, the geologists in the deposits and the mines, trying to figure out what is the right sample and drill core to have in our collection. So this can be a back and forth, we can share data, we can share ideas. Sometimes I leave it up to the geos who are working there and who are far more experienced than I. Sometimes they're like, here's my database, go for your life. So this is a really good process because during that you start to realise what are the data that you need, what are the questions that need to be answered before you start doing any sort of work. And then this happens, which is delightful. So far in the 3 years of this project, we've been able to get 280 new drill cores from Northeast Queensland in our collection, which is incredible. A lot of them are through the Herberton tin field. A lot of them are in the base metal sort of deposits up that way. And now we're moving more into intrusion-related gold. So we're finally getting the right sort of material to do this research on. When we don't have drill core, which is quite often, or when we have to go on salvage missions, you get what you get, yeah? I say it to my daughter, you get what you get and you can't be upset. So it doesn't always come in the right amount, the right size, the right condition, but we will preserve what we can. I feel like as a department, it's really important not only to be holders of like the data and knowledge for Queensland, but really to be preserving the samples. So we put a lot of work in. We have a lot of people in our core sheds who will retray and salvage what they can from drill core, so we can say, yes, I have a bit of this deposit to show you. And then sometimes we get to go out in the field and collect samples. So for the old gold fields and the tin fields where there's just no drilling, we just make do. We just do surface sampling and we just do less samples, but we try and get the spatial coverage so we can say, hey, there's something about this area, it's interesting, and then we can follow it up hopefully with someone does some drilling to do some more in-depth studies. So what's the GSQ workflow? So for those who were here yesterday at the workshop at EDC, Elena sort of stepped through this. The things with the stars are what I've been doing so far in my project. So we're really at sort of bulk mineralogy and bulk geochemistry, and dabbling into in situ analyses and XRF mapping. But really, I'm just trying to get as much data from a few examples of drill holes from each deposit across the whole region, and then we can start talking about what matters. So what have I acquired so far? We've acquired 18 kilometres of drill core scanned for Highlogger, which is about 130 drill cores so far. For mineralised, we were able to do about 9 kilometres of scanning, which was a lot of drill core. And a lot of the things that went through mineralised were drill holes that we weren't able to do destructive sampling on. So while we're not getting the same precision with the analysis, we're able to at least expand the knowledge about that. We've done over 600 samples so far for multi-element geochemistry, and we do a wide suite. I analyse for everything under the sun because I feel like it's good to have that, and then we can start figuring out what matters in these systems, and then as we step out, which methods we continue to do. And we've been dabbling in doing TEMA, and I've done about 50 samples, and that was in places, especially up in the tin fields, when I wasn't able to do other destructive work. So this is just an example of the type of data that we collect. This is from Balgammon, which is a tin, copper, indium deposit, and it's just an example of the power of the sort of data that we're collecting. So tin is an early phase in these systems. It's really hard to see. Often it's overprinted by 2 different base metal phases, and so the Highlogger is really useful. So you don't necessarily need to worry about what the labels say. Have I got a laser? I do. So you have to look at this one over here. This pale yellow in here is indicative of topaz, and topaz is one of the minerals that you see in the tin Greisen system. So we've been able to map and see where the alteration is for the tin mineralisation just by putting a drill core of any, not even the best condition through the Highlogger, and then we're able to step, 500 metres, a kilometre away and look at some smaller prospects and see, are these part of the same system? And Highlogger then shows that, yes, in a smaller scale, you have a couple of metres of topaz alteration and tin mineralisation. So it's been really interesting to sort of use Highlogger data to try and map these systems as you're stepping away. Another useful data that we've been collecting is the mineralised data. So this is a drill hole from a gold field in northeast Queensland, and they assay for gold, which is great. It's a gold deposit. So what we've been doing is able to compare it with mineralised geochemistry, which can't see gold, but can see a whole bunch of different sorts of elements. So I just plotted a few things up that I thought would be interesting to compare to the gold. So moly and bismuth and lead and copper. And then as you can see, we can start to see what is related to the gold over here, or there's a moly kick. What's happening with the gold over here? Well, there's some kicks in the moly, and maybe you're seeing a bit of copper up here. So while it's not exact quantifiable data, it's really useful to start seeing what are the trends that matter. What are the things that we need to be thinking about when we're going then to collect the multi-element geochemistry, so we can be really smart about what samples we do destructive work on. This is a plot showing actually what happens when you have a ton of multi-element geochemistry data over a region. So this is from the Herberton camp. So that is a whole bunch of small tin fields, a couple of base metal tin deposits in there, and a few tungsten plays. It's a combination of drill hole samples and then surface samples. But what it really shows is just they're a lot more complicated, and a lot more delightfully complicated than I expected. Things that were tin were just not just tin, but they might have been tin copper indium or tin tungsten. And elements that were never analysed actually are seeming to be quite important and quite related to a lot of these deposits. So you can see indium sitting in here, and that's predominantly focused with the base metal veins, obviously, because it comes in with the copper and it comes with the base metal phase at the end of the system. But these deposits have quite interesting signatures that would never have been analysed for. You'd be lucky in these deposits to have tin analysed for, and maybe lead, zinc and copper. So just the power of what we can start to see in these deposits. And then also, where are these minerals? Where's the tin? Where's the indium? What are they in? Are they in things in the waste? Were they mined? Are they in minerals that are like a lot harder to get the elements out of? And that leads into the work that Avish has been doing that you can see on his poster, and we've been starting to doing with other collaborators is the tin in stannite versus considerite? Is the indium in sphalerite versus stannite? What's it in and how does it work? And does it move around in these systems? So is it actually something that's worth looking for? Because just because we have anomalous values of these elements in the deposit doesn't actually mean that they're necessarily something that we can mine. So it's good to keep that in mind, but without this base data, we can't even consider these questions. So some of the work I've been doing over the last year, we've been focusing moving from the tin fields and going south into intrusion-related gold systems. So these systems and all the variants that I'll also show in the next plot, on the next slide, essentially have all the elements of interest and a whole bunch of critical minerals that I've sort of snuck in as well so we can talk about gold. For intrusion-related gold system, there's a whole bunch of things that are important. There's a really strong relationship with the intrusive suites of the Permian and Carboniferous, and a lot of really good work has been done on this in previous projects through JCU. And then as Matt talked about earlier today, there's a big solid geology program happening in the Georgetown, Croydon area, which we're sort of trying to address, getting some more information on the potential related intrusives to see where else could we have this type of mineralisation. And the other thing is geochemical zonation. So we're focused on the geochemistry part of this project because there's, like I said, lots of really good geocon out there. So this is a beautiful figure. I'll show this all the time. Lots of people show it. Greg Morrison put it together back in 2007, and it just shows the variety of deposits in the intrusion-related gold systems. You have down this side here, depth of emplacement here, so you're going from 1 kilometre to 6, and then along here you have the geochemical enrichment signature along here. So it's just sort of important to see what deposits sit where, how they formed, are they similar to each other or are they different? But when we're talking about these signatures, we still are talking about a handful of elements here. So these are the deposits that we're working on between now and June. It's quite ambitious. We've been working on Ravenswood so far and Red Dome and Mangana, getting them through the high logger as part of our initial workflow, getting them through the mineralised before we start doing geochemical work on them. So this afternoon, I'm going to talk to you about some of the early results and the hints of how nice it is to have some new modern geochemistry on Mount Lation. Oh, there's Mount Lation there. So this is a complicated slide because I stole it from my workshop yesterday, but the most important things are that the Mount Lation deposit is in a whole bunch of permo-carb dikes and intrusives that have intruded into older granites and metaceds of the Ordovician. And gold is hosted predominantly in breccias, so within the Mount Lation breccia unit. And that is this blue area here and this blue area here. There is there's the entire Mount Lation drill hole database that's available in the Explorer 3 Whole of Queensland Geochemistry compilation, which is brilliant, but limited. So there's been some work that was done part of the compilation from Morrison and Beans back in 2007, 2016, where they tried to look at block models and look at the relationship between gold and other elements. They only had 5 elements. Minutes, okay. There's only 5 elements to do so, so it's only really talking about base metals and gold. Complications arrive with Mount Lation because the more and more we work on it, we realise that these different elements that are dropping out are happening in different times. So they might not be paragenically related, but they might just be happening in the same place. So you're seeing these elements stacked on top of each other, and it looks like they're related to gold, but they might just be happening in the same place. They might have been there before the gold came in. So it's a different sort of deposit when you're talking to like a Ravenswood or some other intrusion-related golds, when you can have the source and you can sort of step away from the source and track it. It's a bit complicated that it's in the one place. But we've just got 100 assays that have just come back from Mount Lation, which is really beautiful. And what I've been focusing on and what else but the things that we expected to see with Mount Lation are related. So we've been doing a bit of platinoids as well with the gold. We've been doing fluorine and a whole bunch of fancy, expensive techniques just to see what sticks. Not that much, that was different. But what is interesting that now we've got quantifiable data. So the things that are interesting are that the signature that we talked about up here, which is like gold and silver and there's base metals, bit of tellurium, bit of stibnite, bit of bismuth floating around. Actually, when you get into the guts of it, there is a lot of bismuth. There's 900 ppm bismuth there. And there is 60 grams per tonne gold, and fluorine is almost up to 1,000 ppm. Yeah, that's right, ppm. So it's really interesting, the more and more we start digging into this data, we can actually see what else is related to gold, and then hopefully some of these signatures track as we go further away. So what do the rocks look like now that we have new geochemistry? So just have a look. I like putting pretty rocks up because it's really cool. Interestingly enough, it's really hard to get your eye in to see where gold is. That's why geochemistry is delightful. But sort of we have 4 drill holes through the deposit, and I'm sorry I didn't put the same cross-section in it behind it, but most of it goes through the Mount Lation breccia. But you can see that the breccias vary in class supported, matrix supported and class supported down here, and you can go, in not too far away from each other. You have a lot of bismuth and a lot of gold, and then a little bit of gold and a little bit of bismuth. So there's a lot of variation too. So we're doing some early work in characterising the breccia types, characterising what the ore looks like, and then hopefully we'll do some more work in the next year. So in summary, we're really just trying to get modern exploration data. We're just trying to get new techniques on these drill holes to provide a data set that can help you when you're out there looking for similar type deposits, and then focusing on what does have endowment of critical minerals, whether you can extract it or not. We just like to know what's there. The prioritisation of the deposits that I've worked on so far is really reliant on what drill core I can get my hands on, and how quickly we can get it. So I appreciate, once again, everybody who's given core, and shout out that, hey, if you've got anything lying around, you've got any questions, please come and talk to me. And really, yes, we're focusing on ore and really getting into the guts of deposits. But this will be so important when we try to look at, what parts of the systems are we in a couple of Ks away. So hopefully in the future, we'll be able to expand this work, but currently we're just working on ore and alteration in the guts of things. And thanks, and please come and talk to me if you work in Queensland. I'm keen to share some rocks. Thank you.
Courtney just said, great, no time for questions, but you can hit Courtney up at afternoon tea, so thank you very much, Courtney. The next presentation will be delivered by 3 of the GSQ staff, Dr. Elena Belisova, Dr. Altamini Tarpo, and Dr. Alkis Kontakas-Charis. I think I got that correct. The title of their talk is GSQ Advance on the Microanalytical Front, and I'd welcome Elena to the stage first of all.
Thank you, Evan. Good afternoon, everyone. So today we are going to talk about our work in the microanalytical space. And I think in the last year or so, we've done a lot of work. And that's why we have 3 members of our mineral system team to present it. So we will swap the stage, so not just to keep you awake, but also just to present different aspects of this work. Well, first of all, of course, I would like to acknowledge the contribution of the whole team, and we all pull in our weight to have it happening. But also we have external collaboration to support this work. Without them, of course, it would be very difficult. And Janelle already and Vlad and Courtney emphasized the importance of our collaborative work. Well, the background, I don't think I need to talk about background into huge details because you hear our big task to do this reference collection project work and give just this comprehensive characterization of ore, and not only ore, but alteration and the host rock. And we are going to talk about importance of our microanalytical work and how it will fit into this characterization process, why we do it, how it's important. And that's all is done with the aim, and the big aim is just make sure the exploration industry have some meat to work on. Well, again, my colleagues already emphasized the range of deposits we have both in northeast Queensland and northwest Queensland. So the same maps just to emphasize the range of deposits and how much of these important critical metals we have. And again, in northwest Queensland have totally different style of types of deposits, and we have this aim to characterize them all. So we try to keep this characterization very systematic, so it doesn't matter what system we work, we have very similar approach. We collect the database which is not only systematic, it's comparable, so we can compare different systems and just have a very clearly understanding on the specialization of this mineralization. And the workflow, you've seen this quite a few times, but I'm going to go through the steps of our workflow, starting from the core scanning and down to our key topic, which we are going to present here, showing our results of our microanalytical work. So as you can see, in terms of the core scanning, we have HiLOGA, which is our main instrument. We have also Mineralizer, which was mentioned several times. And we have very spectacular talk on petrophysics from Roger and how it works. The next step, this instrumentation gives us a very good information for our sampling for the multi-elemental whole rock geochemistry. And this is not a cheap exercise as well. We need to make sure we sampling very right sample for this geochemical work, but then also using this combined information on the core scanning and whole rock geochemistry to target even further zooming down for our microanalytical work. So how, when we do our microanalytical work, it's a huge number of different instrumentation we use. Again, that's where our collaboration is so critical and important. We couldn't handle it on our own. So that's how we achieve it. We have people working on a range of projects, and particularly important collaboration with the universities, where the research project, PhD research project, honors project, postdoc projects are fitting nicely in our work, and they can work on our samples, and they can help us resolve these important questions we have. So it's just big thanks to all these people contributing to this work. I would like to start how useful is HiLOGA for this workflow. And if we look at the results of the HiLOGA, just an example for the drill core from the Dougal River, straight away, even not seeing the labeling, you can see a very distinct lithological domains. So it's a first step when you don't know the deposits, but you already can look at the results of the HiLOGA and see this lithology. So you already have a first step when you're thinking about your sampling. So we're not missing any important intervals in this sense. But also, when we're talking about the footprints of these deposits, we're thinking about alteration. So the HiLOGA is the key instrument which will highlight, this area you can't miss because it's your footprint signatures. And if you wouldn't have, can you imagine you don't have this HiLOGA data? You have trays with rocks. Do you see any alteration here? Can you guess, is it albite, sodium alteration, or potassium alteration? Can you? I wouldn't bet. But having the high logger data, you can see this particular tray represent this albite alteration zone. And the other one, which is quite indistinct. Look, it's very gray. It's, you wouldn't pick it up as important, important interval. But still, this is presenting you with the potassium alteration in this deposit. Another aspect we are looking, you've seen quite a few of those multi-elemental whole rock geochemistry data. So here we just have a comparison in the trace element distribution and critical metal distribution through different types of deposits. But we know it's there. But where exactly it's sitting, where this critical, how it's distributed, is it sitting in one mineral? It just scattered across, we don't know. So without this next step of microanalytical work, we can't answer this question. So that's where we come to this microanalytical work. And Tornado, one of the instruments we just got a few months ago, and Alkis now will take over and just give you an overview of this instrument and the data we collected to this day. Please, Alkis, come over.
All right, thanks, Elena. Okay, so this part of the talk will really just be showcasing what we can do with our new fantastic micro-XRF scanner that we recently acquired. So those of you that were at the workshop yesterday would have seen it in action. But for this part of the talk, I'm going to go into some more detail about our actual applications, which are relevant for a lot of the projects that we do as part of the Mineral Systems team. So the images on the right there, you've probably seen them a lot of times before, but this is the first sample we ran on the Tornado, which is one of Bill Perkins' old samples from George Fisher. So moving on to some of the specs, I don't want to dwell on this, but the Tornado has two X-ray sources, rhodium and tungsten. We tend to just use the rhodium as the finer spot size. And that spot size is about 20 microns, which is perfect for line, spot, and 2D scanning. So the image on the right there is from Pegmont, which if some of you have seen the poster outside, it's a very familiar image. So that scan took about 10 hours. We normally run the scans overnight because we'd like to keep the machine open and available during the day to do active sampling, which I'll talk about later, and Tamini will go into some more detail as well. So it's a non-destructive tool. You don't really need much sample prep other than a flat surface. The maximum scanning area is 19 by 16 centimeters, but the stage is about 30 centimeters, so you can actually put larger core on there and just scan a representative section of that. The Tornado is not a new machine, it's been around for a while, but we've got the latest version, which allows you to measure up to fluorine and even up to carbon with a helium purge. So one of the good things about it as well is that you can actually differentiate between K-alpha and K-beta lines, which is really useful for certain element interferences such as cobalt and iron. So going into the application side of things, so one of the main reasons, or one of the main applications for it is to validate existing data. So this data might be from HiLogger or multi-element geochemistry. We also use it to provide detailed insights into paragenesis of ore and alteration samples, as well as for active sampling in terms of looking for different mineral generations or populations and targeting for geochron as well. So all these three applications really help us to advance our understanding of geochemical and mineralogical signatures of ore deposits, which is something that's at the forefront of what we do in the Mineral Systems team. So starting with an example of validating existing data sets. So this is some geochemistry from the Rocklands IOCG deposit, which is located 15 kilometers northwest of Cloncurry in the Mid-Akuti domain. The map on the right just shows the location of drill holes relative to the Las Mineralis and Rockland South ore bodies. So you see the plots show cobalt and copper, so copper in orange and cobalt in blue. And we can see a trend where both are quite positively correlated around, I guess, 275 meters in depth. But then at about 300 meters, we see a clear discrepancy in the chemistry. So we want to see what's going on with the cobalt. Where is it? Why do we have this trend? So we can take a sample to the tornado. So this is just a basic image of this sample that we're analyzing. So it's just actinolite, magnetite alteration with some chalcopyrite and pyrite and carbonate. So first of all, we can generate these false SEM BSC images, which is used by selecting energy regions in the tornado, sort of just recreating a map based on, I guess, density. So you've got your lighter elements in the darker colors, and also vice versa. So we can then create these multi-element distribution maps. I'm not sure if you can see the elements there, but basically you've got your pyrite in yellow there, copper, or your chalcopyrite in orange, and actinolite in the pink. I haven't plotted iron because we normally use iron as in red, but there's some interferences in color. But iron, the magnetite is essentially the black in this case. So we can then generate cobalt heat maps, and it's pretty obvious to tell from this that the cobalt is entirely within the pyrite. And you have some sort of zonation there. You've got cobalt-rich cores and then depleted rims. But the software on the Tornado also allows you to, it also has some inbuilt plotting options. So these allow you to actually plot relative pixel intensities from the whole coverage of the map. So here you can see the highest cobalt is generally associated with the lowest copper, and there's also a decreasing negative trend there. So we can say that this is pretty much supporting and validating the geochemistry trend that I showed in the previous slide. So we're also attempting to export this raw data and then potentially plot it in something a little bit more user-friendly, such as IOGAS. So the next application is in paragenesis. So here's just, it allows us to see relationships that we might not see with our eyes, or even identify minerals that we can't necessarily identify. So a rock from Cloncurry, not going to give any more information. Just what can we see here? Well, we got some iron-stained feldspar. There's probably 2 generations, or 2 types at least. Probably a chlorite vein running through here. Oh, you can't actually see my mouse. Okay, well, that's all right. Then iron oxide as well, and some late. Okay, now you can. Thank you. So and late carbonate and sulfide veins running through here. So let's take a tornado and see what we get from it. Now I can't actually go to the next slide. All right, thank you. So we have a chlorite vein running through here. The feldspars are actually albite in this case. So I guess the more salmon pink feldspar in this case was the albite, but also the red stained feldspar was albite too. So you can remember from up here I showed in the previous slide there was also a red stained feldspar here. But there's also late K feldspar, so you wouldn't be able to tell that based on just looking at the sample. At least I couldn't. So we also are able to, I'll just use this from now on. We're also able to see things that we might not otherwise be able to pick up, which is these apatite grains within the carbonates. So obviously you can use these for geochronology, for example. Moving on to the next slide, so another example here, another rock from Cloncurry. By the way, that last sample was from Little Ava. But this sample here, we've got maybe 3 types of feldspars. Again, we showed this sample yesterday in the workshop, and I had people try to guess what they could see, and a few of them got it, but it's 50-50. So we also have actinolite running through here, and again, late carbonates. So we've got white feldspar, dark red, and salmon pink. So we take that to the tornado, and in the end, that white feldspar is actually albite, but the dark red feldspar is also albite. So then we have this later salmon pink K feldspar running through. So this is really important for context and paragenesis in deposits, because these are associated with different stages in the deposit formation. So there's also a narrow halo of albite forming along the late carbonate veins too. So this really just shows the complexity that can be revealed from the tornado. And this sample is from Ernest Henry, which is it's at depth, about 1 kilometer in depth, about 300 meters to the east of the copper shell. So this leads me into one of our projects, which Vlad's already spoken about, which is distal footprints. And so we use the tornado a lot to select the right generation of alteration phase or whatever phase we're targeting. So just a brief overview of some of the textures we see at Ernest Henry, and you'll notice that we do have multiple phases occurring at different stages of the deposit too. So we really use the Tornado here to target specific phases, and then we can go to the mineral chemistry of that and see whether or not we can find fingerprints. So really, really useful, and extremely pleased that we have the Tornado to do that. So the third application that we use it for is to active target for geochronology. The image on the left here is of the high-grade ore breccia at Ernest Henry. So it's just dominated by magnetite. You've got sulfides, then K-feldspar clasts. So the K-feldspar in this case is red stained again, probably from hematite dusting, but it can also be variably barium enriched. I wasn't actually targeting that when I scanned the sample, but in the end it revealed that we have these coarse scheelite inclusions within the K-feldspar class. So this might be something that we would take to the next stage and do further microanalysis. Image on the right is from the same hole. Oops, I revealed it already, but well, it's apatite. It's pretty obvious. Actually, no, that the arrows are on the wrong space. I changed the slide last night. Anyway, so biotite magnetite alteration cut by carbonate apatite veins. So again, these apatites are really, really coarse. We can target those for geochronology as well. So I'm not going to go into too much detail on that because Temini is going to be talking about that next. So we've also sent some samples off to CSIRO to do some Maya mapping. Maya Mapper is also XRF, a little bit more high intensity, and spot size about 30 microns as well, and probably has slightly better detection limits for certain elements, particularly gold. We've sent some samples off of intrusion-related gold systems, which Courtney spoke about earlier. So we're also delving into LIBS, sending some samples off to AXT because we want to see whether or not we can include this into our workflow. But still emerging technology. It's really useful for light elements and also has a pretty good spatial resolution as well. So really keen to see the results on that. Hopefully we get them maybe in a month or two. But moving on to the take-home messages. And the first one is that we are pretty advanced now at GSQ in terms of core scan techniques. I know it's just HiLog on Tornado, but just with Hyperspec and XRF, I feel like we get a lot of things answered and we actually find new questions from those data sets as well. And yeah, we're experimenting at the moment with Maya too, and LIBS, and of course Roger spoke about the MPO. But in terms of surveys, government surveys, I think we're pretty well placed. So Tornado has revolutionized our sampling protocol because it allows us to screen samples and not just take everything to the next step, because the next step is time consuming and also very expensive. So if you take samples to TEMA, it's a lot more money involved, and also you don't really get a big sample area. You could just get these 1-inch rounds or a thin section, for example. So having the context of the sample is really important. So ultimately, all this allows us to advance our knowledge and understanding of geochemical and mineralogical signatures of ore deposits, which of course can lead to more discoveries in the end. So that's it from me. I'll pass on to Temini to talk more in detail about some geochronology. Thank you.
Thank you, Elkis. That was a great overview of the Tornado instrument. My talk is very short, and it's basically focusing how we are using Tornado as an active sampling instrument, and mainly focusing the geochronological aspect, because geochronology is a really difficult thing. You know, the sampling has to be very precise and very reliable. So we have taken up an example from one gold project from Northeast Queensland, which is intrusion-related gold, epithermal style. And you can see on that left image, that's a mineral map. So Tornado can produce the elemental maps, but we use a separate software that is AMIX that has got a built-in library of 5,000 minerals, and we can produce mineral maps out of it. And you can see that the gold is mainly associated with arsenopyrite, and arsenopyrite is rimming the pyrite grains. And in this intrusion-related gold, we have got two quartz vein phases, basically, and the early stage, which is gray quartz, and the late stage is white to pinkish quartz. And the late stage quartz contain high amount of gold and sometimes visible gold. But that's about the overall mineralogy of it. And the alteration is mainly sericite. So basically, the ore-bearing fluid was altering the host granite rock. All the feldspar populations, they became sericite. All these green minerals there on the left image, you can see those are basically sericite. So the key objective of is to test, can we use the Tornado as a reliable sampling protocol? And for that, we have got two candidates here, our host rock and the alteration phases. The host rock, it is typical in granite, so we'll be targeting definitely zircon for iridium-lead dating. And for alteration phases, we'll be obviously aiming for sericites. But there would be multiple populations of sericite, and which sericite we are going to target. And also for zircon, because we are dealing with a very small quantity of samples, is it enough for mineral shape, or can we target a specific area of a drill core for in situ dating? Let's have a look. And those are the grains we have picked from the for argon-argon geochronology, basically, by using the Tornado instrument. So I'll start with the host rock. In this image, you can see these like two inset boxes, A and B. And on that rightmost image, you can see there is that dark pink showing the zirconium, and the blue is the aluminum phases. So here, we have identified that the zircons are actually mainly associated with aluminosilicates, that is mainly biotides. And particular areas of this scanned area in this sample have higher proportions of zircon hotspot compared to the rest of the sample. So, and also the amount of zirconium hotspots are not that high. So this sample is probably not a great one for mineral shape and for further geochronology studies. Instead, we can use those areas for thin section prep or for blocks, and use them as laser ablation iridium dating. And then for the mineral, for the ore body, the ore fluid or the alteration dating. So we have so far identified two types of sericites from our visual inspections, which is dark green and pale green. But which one of these populations are a better one compared to each other? So again, we did some Tornado map plus some spot analysis. I'll be coming back to the spot analysis. And you can see some of the elements, some of the analyzed places have got higher titanium in it, and some of them has got very homogeneous signatures. So what we found, the pale green sericites here are more homogeneous, have less inclusions, and have less secondary alteration signatures, whereas the dark green ones has got more inclusions, more altered. And also the inclusions, so these are for mainly argon geochronology. So some of the mineral phases can affect the results in argon geochron. So for that, we have to be very careful which type of inclusions are there. So what we have found, the pale green ones, they have got mainly magnetite-like inclusions, which doesn't affect the argon geochron that much, which is another positive side. So we have picked the pale green, obviously, from these Tornado scans. And again, not only the alteration phases, we have also targeting the crystalline sericites, that is vein ill fields. So how do we identify that? It is really difficult because most of the rock, all the products looks green. We can't do that using only the visual inspections. So again, we ran it in the Tornado, and you can see in that black box there, some of the sericites have these yellowish pixels in it. So the yellow indicating the sulfur. So the crystalline sericites, they have got this higher sulfur content compared to the altered product that is in that right-hand image where most of the sericites are boringly green. So this also gives us a really nice contextual information which sample we can reliably choose for the better geochronological work. And just to summarize, so we can do really develop our own paragenetic sequence or test the instrument and the sample for reliably sample selection for the geochronological work. And also the single and multi-element combination maps are really helpful to identify this kind of scenarios. And in addition to that, Tornado cannot resolve all our questions. It cannot answer all of it. So we need more high-resolution work for the selected samples, and that is possibly TIMA. And Elena will be talking about the next step we use, that is mainly TIMA, and also she will be discussing a bit more about how complex the geochronological work is. Thank you.
I hope you're happy to see me back on stage, but I promise I show some nice photos, nice pictures. Well, now you can see what we can do with our Tornado instrument, and this allows us really targeting this more detailed work using the TIMA instrument. So what is TIMA? It's TESCAN integrated mineral analyzer. So what it combined backscattered electron and EDX analysis to identify the number of the element distribution, to create the similar element distribution maps and also the mineral distribution maps on a very, very fine scale. So we're talking about the micron scales. One of the great advantage of this, of the data we're collecting on the TIMA, that we can do it on thin section and we can do it on a mounts, and this is standard sort of shrimp mounts, 2.5 centimeters mounts, which we can send straight away to a number of the lab, put them in a machine, and do in situ analytical work. So this is the example of one of our sample from Pegmont, and you can see it's a spectacular compositional bending of the sphalerite, apatite, and garnet. It's not only beautiful to look at, but it's also very useful information on the relationship on different mineral phases, so we can sort out the paragenetic relationship and also target precisely this individual mineral for our trace element, in situ trace element work, or geochronology. Also, the benefit of the TIMA maps results. You can see we have a very detailed and very high resolution backscattered images. We also can create these element distribution maps. We can create the maps for a single element if we're interested, or a combination of the number of elements. It's up to us. So the software is very flexible. You ask the question, we produce the map we needed to resolve the problem. And also, we have a very detailed map showing the distribution individual mineral phases. So when we send these sort of maps to our collaborators at the universities, I think they really appreciate having this information and start their research on a very well documented samples. But TIMA can do even more. So here I show you how we can create the maps of the individual mineral phases overexposed on the backscattered images. So if I ask my students who do all this in situ work, would you like to have a map of this and don't spend 2 hours looking on the right mineral and still doing mistake analyzing some wrong mineral phases? This is the brilliant example where you can really target the mineral phases and do resolve. If you have a question, for example, here we can do geochronology on apatite, and we can do geochronology and trace element work on the garnet. And we also can look at this sphalerite, which is in the same sample, and look at the composition of the whole range of trace elements using ICP-MS analysis, including these important critical metals we're talking about, like indium and germanium. So we are well prepared to distribute a huge number of samples we were working in into the range of universities in Australia and possibly overseas if needed. And another very important aspect when we look at these detailed TEMA maps, if we, for example, decided to target the appetite, it's not always it's a single appetite we have in our sample. This is a good example where we have, I have a zoom in area. If you can see the speckles of the greenish colored appetite, it's present both in the host rock and it's also closely associated with this mineralization vein with chalcopyrite. So I bet it would be two very different population of apatite. So if you crash this rock and extract your apatite, you will be having a lot of trouble to do interpretation on your results on uranium lead dating, for example. Here we can characterize these distinct populations and we can date knowing what we dating and where this apatite crystallized. If it came with this mineralization fluid or it's pre-existed in a host rock, you know, billions or millions years before this mineralization formed. Well, and talking about the dating, dating of mineral deposits, it's very challenging task. And we have seen that some of the deposits are related to the magmatic intrusions, some of them really closely associated with metamorphic or hydrothermal processes. So I guess our microanalytical work, this really help us to identify the minerals which are really reflecting these processes. And also we just can clearly understand what minerals to use, which isotopic system to use, so we have exact timing or even the whole range of ages just to characterize this evolution history of the deposit. We're also doing some direct dating of the ore, and currently we have a project with the PhD student, for example, using the cassiterite for uranium lead dating. This project is done at the James Cook University. We also just established the project with Curtin just to look at the rhenium osmium dating of the sulfides. So hopefully next year we have some real outcome of this multi-states project and on the microanalytical work and some geochronology and trace element work. But here, just to summarize, just to show you the extent and whole breadth of work we are doing, just to show you what the deliveries we are planning and what was already done and published. So this is just a summary for Northwest Queensland. We couldn't probably fit everything for whole Queensland, but it's just to give you an example how many deposits we studied, what type of the deposits, and what kind of work was done. So you can see that the high logging was done for all of these deposits. We also, the majority of our mineralizer, the majority of those deposits have some data collected using mineralizer. We also have extensive now data collection characterizing the whole rock geochemistry, and bulk of this data already was available and released last year. So now we have, you can see the last column where we have ticked work which was done in microanalytical space. So this data is really close to the publication for the data release. So hopefully in the next couple of months you will see it out and available on our JSQ data portal. And just to give this sort of larger summary, what we are doing starting from the core scanning, from macro scale down to the micro scale on these, small samples, it just gives us a better information on the fingerprint in this trace element and isotopic signature of this mineralization-related system and fluids and mineralization system. So we can have better understanding on the distinct sources and can discriminate between the different type of deposits and also refine the timing of this mineralization. Importantly, we also want to have this better understanding on geochemical vectoring. So hopefully all these pre-competitive data, which will be available on our JSQ Open Data Platform, will help the industry for more efficient and effective exploration targeting. Thank you.
Thanks very much, Elena, Alkis, and Tamini. We're on to the last talk for this session. I'd like to welcome to the stage Dr. Ben Hines from GSQ's Mineral Systems team, who'll be speaking on critical minerals in Queensland's mine waste. Welcome, Ben.
All right, g'day everyone. I'm very conscious of the fact I'm the last man between you and coffee, so I'll try and keep this high level and get it out the door. All right, so several of the talks today have sort of picked up on these themes of critical minerals and also mine waste. So, we had Tony and Aaron, Sean up here this morning, all drawing upon those threads. And we also had Janelle up here before talking about our collaborators, so different institutions we're working with, and that's a good way to introduce the Sustainability Minerals Institute and the MyWatch team at University of Queensland, who have done a lot of the grunt work on the secondary prospectivity project, which I'm talking about today. Right. All right, so because Aaron covered this in some pretty good detail this morning, I don't need to go into it, but what I will go into is just a very quick definition on critical minerals and new economy minerals. So it is names, but whereas critical minerals are pretty well defined, for example, Geoscience Australia publish a list every year, and one or two get bumped up or moved around. We tend to use the phrase new economy minerals because it incorporates other elements which may not be as rare or as critical as the term critical minerals implies. But they're still very important for the green or the emerging technologies sort of revolution. So, picking up on our critical mineral strategy, which Aaron introduced this morning, this is where we fit in. So, first of all, we're facilitating secondary prospectivity of deposits within Queensland, and that also feeds into research and development of a circular economy in Queensland. So by reappropriating those mine wastes, reutilising them, we're helping to deal with a little issue there. So what's our endowment? So we've got more than 13 or so minerals demonstrated up here, but we've got a good distribution across the state as well. So we're very well endowed, we're very fortunate, and that creates a lot of opportunity for us. So not the first time you've seen this map today, but it does give a pretty good indication of what we've got and where it's situated. And even if you're looking at the distributions there, you can already sort of draw upon a couple of relationships that you can see. You see that co-occurrence of copper and cobalt, maybe some tin tungsten associations, etc. And that's something that we can feed into our deposit models later on. So, talking about the New Economy Minerals Initiative, which is where the secondary prospectivity project falls under. This is a GSQ scheme that was kicked off in 2019, and it officially runs out next year. So that's split into two streams. We've got the hidden value and the new exploration. Under hidden value, we've got deposit characterisation, mined the core and old mines new value. So I've highlighted deposit characterisation and old mines new value because they sort of fit into the secondary prospectivity framework. So yeah, if you're looking at utilising mine waste, a really good way of looking at that is as another deposit style. It's an anthropogenic deposit, but often not characterised. So we might know the primary commodity that went into it, but we don't know actually the strategic or critical minerals that may be incorporated there. And I mean, old mines new value is a pretty obvious feature there. And I've highlighted prospectivity under the other stream. I mean, really, you could also apply many of those aspects if you're going to take that deposit scale approach to evaluating mine waste. So I've borrowed this one from Helen via SMI, I think, so apologies for that, but I just really want to, I reckon this image in the centre here really hammers home the point that mine waste is a significant issue. So focus on the blue dots. Those are inactive mine sites across Australia. There's a couple of little data representation issues where, yeah, I think Victoria and New South Wales are over-representing their data sets. You know, they're including quarries and what have you. But it still paints a picture that this is a pretty significant feature in the Australian landscape. So, in regard to Queensland, what does the opportunity look like? Well, what we've got more than 50 active mines, but we've got more than 150,000 registered abandoned mine sites. So we've got a pretty good playing field to start with here if we're going to start looking at secondary prospectivity and mine waste. Of these, 317 are of the medium to large scale sizes. So that would be a pretty good starting point for us, and it provides the foundations for the secondary prospectivity project. So as a quick aside, a bit of a case study, you've got Mount Isa here. It was mined for cobalt in the 90s. There's reported spot grades of over 9% cobalt, and there's currently no public resource on cobalt there, but we do know it's a thing. And if you look at the tailings dam in the image on the left here, sorry, you're right, we've got 15 square kilometres of tailings, so we've got a pretty substantial volume there. And I was talking to Tom Evans yesterday, who sort of made the passing comment that, this probably represents the largest cobalt resource in the Southern Hemisphere. So if you really want to make a case for secondary prospectivity, I think that's it. All right, so the secondary prospectivity project, we've got a pretty well-defined, pretty clear problem. And breaking that down into some project aims, we can extract 4 here. So first of all, we need to characterise what we've got. So actually, what do we have? What critical minerals do we have? And we don't really know. So we need to know where they're located, what systems they're associated with, and we need to actually just get out and define it. That's where SMI have really pulled in and done the grunt work. Actually, all of these 4 points, I should clarify that. We also need to define the relationship there. So it's not a matter of knowing how much of what element where, but also what it's in, what it's associated with, and how to extract it. And then the third and fourth points sort of speak for themselves. It's developing new analytical technologies, or maybe applying existing technology in different ways, and also developing new processing techniques. So those 4 objectives can be boiled down into 3 streams. And again, this is a breakdown of something Anita presented a while back, because it's a very short, sharp summary of these points. So the research group at SMI have divided it into 3 project streams. So you've got stream 1, which is your first pass assessment of these sites, and we're aiming to achieve 24 sites by 2024. And yeah, that's your first pass, basically geochemical characterisation and ore characterisation of those sites. Of those, a handful of sites are getting selected for, or have been selected for, some detailed investigations, so much more comprehensive work. And then finally, under stream 3, it's more about developing new ore processing technologies, so how to better extract critical minerals from those ores. In terms of locations sampled, so across all 3 streams, 29 sites have been sampled and counting. 25 sites have been sampled for stream 1, so that's your primary characterisation stream. And and both sites have been characterised for their critical mineral endowment. And there's another 4 to 5 sites currently underway or sort of being assessed for future work. So to date, there's been over 2,200 samples collected. And from here, I'm just actually going to be focusing on stream 1. So in terms of the mine waste styles sampled, most people think of tailings and waste rock, but there's also a few other waste styles that can be sampled here. So these include spent heap leach piles, metallurgical slimes, slag, so from smelters, and also fly ash from coal power stations, as well as bauxite residues. So we had a crack at most of those so far, and we're just trying to knock out the last few. So the workflow, very straightforward. So you sort of review the existing data sets, do your site selection, work out if it's got the scale and scope for particularly critical minerals. And then it goes into sample collection or selection. So some sites have already had a bit of preliminary work done on waste rocks by private industry. And then we go into the sampling regime. So generally in the ballpark of 40 to 80 samples are analysed for bulk rock geochemistry. That's by a 4-acid multi-element method. And then from those, the top 10 performing samples are run for bulk mineralogy by XRD, and also for microanalytical methods, which may include reflected light spectroscopy, mineral liberation analysis, and X-ray laser ablation ICP-MS. Hopping into some of the results, so most of you would have seen the cobalt results before. This is sort of the pilot where this project started, and really pulled up these 3 key players here. So we've got the Great Australia, Osborne, and Rocklands showed really good results there. And I'll just point out that the average crustal value is about 30 ppm, so these are well in excess of that average crustal value. If we look at indium, we've got a real clanger at Balgammon there. Oh, sorry, at Herberton, sorry. And we also have a good result from Balgammon, and some fairly good results from Mount Garnet and Mount Morgan. Notably, the average crustal value, crustal abundance of indium is about 0.1 ppm, so exceptionally low. So you see a number like 18 ppm is pretty good. Total rare earths, so this is expressed as total rare earth oxides. And yeah, so the data set here is fairly representative. So yeah, the data average is within Kiwi of the average crustal abundance, with the exception of, in particular, Merikathleen, which has a cracking result at 1.8% total rare earths. And then, yeah, 2 other sites as well, Pandora and Wolfram Camp, coming in at 0.1%. Looking at tin, we can see 3 standouts here. So again, Balgammon, Collingwood, Herberton, all within that Tableland region, inland from Cairns. So well-known tin district, perhaps not surprising, but good result, yeah, pretty interesting results nonetheless. Into moly. So the only real standout of moly was Wolfram Camp, and also for tungsten. And again, excellent grade, 1.1% on tungsten there. But not surprising given the history of the mine, so that's where site selection is important, but it's also where the opportunity lies. So the fact that there's metallurgical issues with trying to separate moly and tungsten at Wolfram Camp sort of creates plenty of opportunity within a waste rock story here. Just quickly touching on some of the microanalytical methods. Very hard to express this, but this is an absolute gem within these reports. So the MLA basically provides a breakdown not only of the grain size, but also captures the mineral components that you're looking at. So you can actually break apart what ore minerals are present and the size fraction they're captured in. And then following on with some laser ablation of those same samples, you actually understand the specific mineral phases that these critical minerals are captured in. So this is kind of like having your MET work done, or your preliminary MET work done from the very offset. So it's really great for scoping and feasibility of these projects. So, yeah. All right, in terms of data availability, it's all getting up there. It's all online. Well, no, sorry, it's getting online. So the Cobalt reports, which came out initially, are up there. And also some initial scoping reports on the secondary prospectivity project and various critical minerals on the NEMI page. So check those out, and there'll be more reports coming soon. Again, I just really want to acknowledge the contribution from SMI, who have put all the hard work into this, but also to the tech services staff who have, in many cases, gained access to some of the more restricted mine sites, the abandoned mine sites, or gotten out and helped with activities as well. So yeah, thank you all.
Thanks very much, Ben, and please join with me in thanking all the presenters for the third session. Thank you. I'd now like to welcome Janelle up to the stage to do some announcements regarding the posters.
So I have the great pleasure of announcing who our poster prize winners are for the session. Thanks to everyone who voted. I will make a note that it wasn't just student posters, but also early career researchers. I think it's important to amplify the work of both of these groups of people. So without further ado, in third place, I have Jenna McGovern for your poster. You win a prize. You'll have to come up to the stage and be photographed. I will note that the voting was very, very tight, and at one point we had a four-way tie for third place. So anyone whose name is not on this list, rest assured your poster was also very high quality.
Thank you so much.
We're gonna have to have
cool. Okay, no worries.
All right, in second place, we had Alanis Oleshburn. I'm sorry, I mangled your last name. Are you still in the room, Alanis? I'm sure it'll be very exciting taking a book that large on carry-on baggage, but I'm sure she'll manage. And our first prize winner is Enrique Salgado. I'm so sorry. And I was practicing, you know, and I knew I was going to get it wrong, but I tried really hard. Congratulations.
Thank you so much.
All right, I'm aware that afternoon tea is outside waiting for us, so can we have another round of applause for all of the prize winners and everyone who submitted a poster? And it would be wonderful to get a photo of the winners with their posters so that we've got a record of, you know, the wonderful work that you're doing in this space. So I'm going to release you all to get some food and some coffee. I think we're back here pretty quickly. At 4. At 4. 2 more talks to go, people, and they're about how to get money. You want that, don't you?